Welcome to a new video in our series, A Beginner's Guide to the C Programming Language. In the last video, we discussed some miscellaneous topics in C. These included the enum declaration, type defs, and command line arguments. We now move on to the next section of our course, where we will discuss the core features of C. Please like and share this video, follow our channel, and subscribe for notifications on new videos. In this video, we will cover storage classes. A storage class is a declaration of the memory area in which variables are declared. The C language allows developers to create variables in different areas of memory, where they can be initialized and created with temporary or permanent lifetimes. A C program uses internal memory to store and process data. Every program is allocated an addressable memory block for its exclusive use. The memory is split up into code, data, and stack segments. There are three distinct pools of memory to store data. These are static memory, which is used for global variables, the stack, which is used to create local variables, as well as arguments to functions and storing return values. The heap area of memory, which is used for dynamic memory allocation. Static memory is used to contain global variables. These variables are declared outside the body of any function and persist throughout the lifetime of a program. A global variable in C is initialized to 0 and it is accessible to all functions within that source file. A stack is a LIFO buffer or a last in, first out buffer, which is used to store arguments passed during a function call, variables declared within the function, and return addresses of the next statement after the function call. All this data is pushed into the stack. The stack pointer, which points to the top of the stack, is incremented as required. Variables declared within the function are also allocated memory in the stack. Note that these variables are not initialized after creation and need to be explicitly initialized. These variables exist as long as execution control is within the function or a function call below it. When the function returns, they are destroyed. That is, they are popped out from the stack and the stack pointer is decremented. In later sections, we will see how to allocate memory dynamically. This dynamic allocation of memory occurs from the heap or the free store of memory. This memory can be initialized or uninitialized depending on the function used to allocate it. A storage class defines the scope and lifetime of a variable. It also defines what kind of memory is used to store the variable. Variables are created and destroyed as needed. This helps in the efficient usage of memory. A good programmer would limit the scope and lifetime of a variable so that it's not visible to functions beyond its scope or retain memory longer than it should. The four storage classes are auto, which are used to create local variables. They are temporary variables which are created on the stack and uninitialized if not specifically initialized. The next storage class is register, which are special kind of auto variables. They are assigned to an internal CPU register. Register storage class is used to make the code more efficient. If an internal register is not available, then the variable is allocated on the stack just like an auto variable. The third storage class is static, which are used to declare variables in static memory. As mentioned earlier, static memory is initialized to 0 by the startup routine of the program. Static variables can be local or global and behave differently, as we will see later. The final storage class that we will discuss today is extern, which are used to link to a variable that is declared globally in another source file. So let us have a look at each of these storage classes in more detail. The storage class auto is a default storage class for all local variables. The storage class auto need not be explicitly mentioned. Auto variables are created on the stack and have the lifetime of the function and are visible only to those statements within the function. As shown in this example, we have defined two functions, max and min. Each of the function declares an auto variable, int max and int min respectively. The variables are created when the function is called and destroyed when the function returns. Also, they are uninitialized and can be referenced only within the statements of the function and not outside it. The parameters num_a, num_b, and num_c are auto variables as well. The storage class register is also used with local or auto variables. When a variable is declared with a storage class of register, the compiler will attempt to assign a CPU's internal register to that variable. Declaring a register variable makes the program more efficient since the CPU does not need additional fetch operations to read the data from memory. It can perform operations on the variable directly since it already resides in the register. Typically, you would use the register storage class for frequently used variables like counters, flags, etc. Note that even if you declare a variable to have storage class register, it may not be possible to assign a CPU register to it. In that case, the variable will be stored in the stack as usual. As shown here, in a 16-bit compiler, you can declare register variables that are max 16-bit wide, like ints and shortints, or 8 bits wide, like a character. The static storage class alters the lifetime of an auto variable or changes the scope of a global variable. When an auto variable is declared with the storage class static, it is allocated memory within the static memory area and not the stack. This means that the variable is created when the program begins execution and exists for the entire duration of the program's lifetime. It is also initialized to 0 and retains its last value in between function calls. However, since it is declared within a function, it is visible only to statements within the function. Thus, when declared within a function, static variables have global lifetimes and auto scope. We will see how static variables affect a global variable after discussing the external storage class. In the example shown here, the function max declares a static int variable maxval. This variable is created when the program begins execution along with other global variables and is initialized to 0. The function max is called 3 times in the program. The first time it is called, it is passed a number inputted by the user. The function max compares the value of the parameter num_a to the value of maxval, which is 0 the first time. After comparison of the two values, the larger of the two values is returned back from max. The second time the function max is called, it is passed a new value entered by the user. Now the variable maxval holds the last value it contained during the previous call to max. This value is compared to the parameter passed and returns the larger value back to the function main. Thus, when declared within a function, static variables have global lifetimes and auto scope. The final storage class is extern. The external storage class is used to change the scope of global variables. As we have seen earlier, a C program consists of multiple source files. Each source file may have global variables defined in it. These global variables are visible to all functions defined in that source file. If you want to access a global variable in another source file, you should declare the same variable with a storage class extern. The external storage class tells the compiler that the variable has been declared globally in another source file. So no memory is allocated to the external variable declaration. However, the variable can be accessed in that source file depending on the scope where it is declared. During the linker phase, the external variable is linked to its global declaration. As shown in the example above, the variable var is created globally in the first source file. If you want to access the variable in the second source file, you must declare it as an extern. No memory is allocated to var in the second source file, but it is linked to the declaration of var in the first source file. This linkage happens during the linker phase. So all references to var in both the source files will access the same global variable. Now let's look at how static storage class changes global variable declarations. We know that global variables can be accessed across multiple source files if they are declared as externs in the files. However, if you want to restrict access to the global variable to the source file it is declared in, you can use the static storage class. In the example shown here, the variable var is declared as a static global variable. Hence, it can be used only within that source file, and it would be illegal to extend its scope using the extend keyword in another source file. In this example, the variable var in the second source file occupies another location of memory separate from the static variable var in the first source file. That is, these two variables are separate variables and can contain different values independently. We have now seen how storage classes are used to limit the lifetime and visibility of variables. A good programming practice is to keep both these to the minimum. Reducing the lifetime of variables enables efficient memory usage, and limiting its visibility reduces the possibility of side effects and tight coupling of code with data. Let us have a look at how storage classes work in practice. As we have seen here, the function main calls the function printf and factorial. The function factorial in turn recursively calls the function factorial and printf. We have declared the variable factval in the function main. This function by default is an auto variable. It is created when the function main is called, and as you can see, it is not initialized at the start. The function factorial defines two auto variables. One is the parameter num, which contains the argument value passed to it during a function call, and the other is factval, which even though it has the same name as the variable in main, is a separate variable unrelated to it. It is also uninitialized. The variable factval in main will not be visible in the function factorial. Now factorial calls itself recursively with a new argument every time, till the argument is 1. Every time factorial is called, a new copy of num and factval is created on the stack. Now what happens to the older versions of these two variables? They still exist, but are not visible in this call. These variables will be visible again when control returns back to that function call. Let's single step through the program. First, observe the value of factval and the call stack window. This is before the call to factorial. The first call to factorial is from main with num equal to 4. Look at the value of factval and num. Since num is not 1, we are calling factorial once again with a value of 3. Observe the value of num and factval. We will repeat this call again with the num value of 3, 2, and 1. The factorial function now returns without a recursive call, returning a value of 1. Factval is now 1. The data is displayed. Now you can see the value of num and factval. Let us single step to return from this factorial function call. Notice where the current execution line is, the call stack window, and the values of num and factval. Note that every time the function factorial returns, its copy of the num and factval variables are destroyed. We continue to single step till the control goes back to the function main with the final value of factval. This is the final output of the program. As you have seen, auto variables are temporary variables that are created when the function is called and destroyed when it returns. They are created on the stack and are uninitialized when created. Now let us see how static variables work. Here we have a function called max, which contains the static auto variable called maxNum. The function compares this value with the value of the argument passed to it and initializes maxNum with the greater value of the two. Let's single step and see how this works. The first time max is called, it is passed a value of 10. The variable maxnum is declared as static, so it is initialized to 0. Then the comparison of the parameter num and the static variable will ensure that the larger of the two is stored in maxnum. Then the value of maxnum is returned. The next call to max passes a value of 5 to the function max. As you can see out here, the variable maxnum retains its old value, that is 10, and thus returns the same value back to the function main. This is followed by another call where maxnum is now replaced with 20. And in the final call, maxnum has the last value within it and then returns the largest value. The function then displays the largest value passed to it in the 4 calls to the function max. Finally, let's have a look at the external storage class. Here we declare a global variable called maxval. We have two source files in our project now. The first source file contains a function main and a declaration of a global function called max. The second source file contains a function definition of max. We also declare the variable maxval as extern so that it is linked with the variable declaration of maxval in the first source file. In the function main, we call the function max as before. Notice how each call to max will initialize the global variable maxval. After the last call to max, the final value displayed is the largest value passed in the 4 calls to max. This is similar to our previous example, only that instead of using a static variable, we have used a global variable. This example also shows you how the external storage class is used. Finally, let's declare maxval as static in the first source file. Now if we build our program, we get an error because the external storage class declaration in the second source file is illegal. This is because declaring a global variable as static means that it limits the scope of the variable only to that source file in which it is declared. We have reached the end of our discussion on storage classes. You should now be able to decide the lifetime and visibility or scope of each variable when you declare them. Thank you for joining us. Please share and like this video and follow our channel. In the next video, we'll have a look at branch statements in C and how to control the execution flow of a program. See you then.